Alright, so we're going to do a sort of revision summary, but for the first time for some of you, on proton NMR. NMR stands for nuclear magnetic resonance. Okay, so this is a tool to identify hydrogen types or hydrogen environments in a molecule. Now, we spent some time in class talking about how it works and some things you need to know about running it. We don't actually need to know those, I don't think, for the spec. We're going to focus on what information you get and what the spectra look like. So the first thing that I kind of remind people is there's 4 things to try to remember when doing NMR. So always remember 4 things, and we're going to go through this kind of one at a time. The first thing we need to look at is the number of hydrogen environments in a molecule. Oops, environments, excuse the spelling there, in a molecule equals the number of peaks in the spectrum. We'll have a look at a spectrum or two in a bit, okay? 2, well, the next 3 are the 3 things that you need to know for each peak. So how many peaks there are, and then for each peak there's 3 things. The first of which are how many hydrogens in that environment, in each environment, and that's equal to the area under the peak, or the relative area under the peak. And that makes sense when I show you an example of that in a second. And so we sometimes call that the integration trace, and that's the language the IB seem to use, okay? Integration trace. The third thing for each peak, or the second thing for each peak, but the third thing you to remember is something called splitting pattern. And that's either going to be a singlet, doublet, triplet, quartet, or multiplet. It's going to be one of those 5 things. If you're really stuck, you can guess one of those. And we'll explain that. It's all to do with the number of hydrogens on adjacent carbons. We'll see when we get there. And the 4th thing is what we call the chemical shift. I'll probably do these in a slightly different order when I go through them. Chemical shift is equal to position on the horizontal axis, and that is values you get in the data book. So part of the work that you're going to do, and the exercise you're going to do, will be getting familiar with the information in the data book as well. Right, so we're going to start off with the first skill, which is the number of hydrogen environments. We spent quite a long time on this in class, but I'm going to do it quite quickly now. And what I'll do is I'll draw some molecules, and we'll just see if we can work out how many different hydrogen types there are. The thing we're looking for is hydrogens that to be one hydrogen environment, the hydrogens in an environment are completely identical. In other words, the view from that hydrogen is the same as other ones, if you like. So this hydrogen, hopefully you agree, is identical to this hydrogen. This bond is rotating around freely, and these hydrogens are exactly the same as each other. So that's all part of one environment, these 3. These 3 are identical to these 3 as well, okay? Because they're CH3s next to a CH2, which is next to a CH3. They're exactly the same as each other. So we say that's one hydrogen environment, but the CH2 on that molecule is a different environment. So there's 2 environments, A and B there, see? So label them A and B and A. Make sense? And while I'm at it, I'll also we'll start talking about idea 2, which is how many hydrogens in each environment. So in hydrogen environment A, there are a total of 6 hydrogens. And in hydrogen environment B, there are 2 hydrogens. You can have this sheet afterwards, so don't feel like you've got to write anything. And so what we see in the NMR, and you'll see some examples of spectra in a bit, the ratio of those, simplest ratio is 3:1. So the areas under the peaks with 3:1 ratio for A over B, right? Let's do a few of those so you're getting the hang of it. So it takes a while for people to get this. I'm going to draw an ester. It's a good opportunity to remind you what an ester is. It's a bit like a carboxylic acid, but with a carbon chain instead of an oxygen. And this ester is methyl ethanoate. Methyl because it's one carbon, ethanoate because it's two carbons. But the whole point here is there are two hydrogen environments. They look really similar, right? Because that's a CH3 and that's a CH3. But their view, their surroundings, their chemical environment is slightly different. So there's two environments there. And the ratio of those is going to be 3:3 or 1:1. So two environments and then a 1:1 ratio when we see the spectra. Okay? So another example. So we're going to draw another ester now. So CH3, CH2. I've turned the ester around this time. This one's a little bit harder. I need to think a little bit harder. So what I want you to do, I'm going to pause the video for a second. I want you to tell me how many hydrogen environments you think there are and show me with fingers. The answer is there's 4 environments. That's one, that's one, that's one, and they're equivalent to each other. So we've got 4 environments, 1, 2, 3, and 4, A, B, C, D if you like, and the ratio would be 3 to 2 to 1 to 6, right? We'll do one more of these so you've got the hang of it. So I'm going to draw an ether now, which is an opportunity to remind you what an ether is. Ether is just an oxygen in the middle of a carbon chain. I'm sure you knew that. There we go, there's an ether. So again, show me with fingers how many hydrogen environments you think there are in there. So again, it's not 4, there's 5. You might think that and that are the same, but they're not. They're similar, but not the same. In fact, they're not even that similar as it turns out. You might think that these are all quite similar to each other, but then they've got to be exactly the same. So that CH2 is next to a CH3 and a CH2, whereas that CH2 is next to a CH2 and a CH2, one of which is next to an oxygen. They are just different. And so we label them A, B, C, D, E. And when you look at the slide, you realise there's a load of examples of this with the answers all given. A, B, C, D, E. 3 to 2 to 2 to 2 to 3 ratio. Happy with that idea? So let's then look at, find a spectrum. We'll look what a spectrum looks like, if I can find one. So here's an example of a spectrum in the work pack. Sometimes the area under the peak is given as a set of numbers, 1.2 to 1.2 to 5.4 to 1.8. This is quite a relatively complicated example. Might want to have all eyes here. I know we've been through this, but if I just show you this one here, sometimes the area under the peak is given as numbers like that. And that ratio, hopefully you can see, we might have to simplify it, well, make it down to 0.6 to 0.6. I don't know why I've done that, I'm adding confusion. I think it's 2 to 2 to 9 to 3. Does that make sense? If you divide them by 0.6, that's what you get. That's what I was trying to do there. So that's a 2 to 2 to 9 to 6 ratio. That tells you how many hydrogen environments in that peak, that peak, that peak, and that peak. The way that you might see it on your exam papers, folks, though, and in the packs of questions you're going to do shortly, this is as an integration trace, which will look like that. So that height must be the same as this one. They're a 2 to 2 ratio. This one over here is going to be 1.5 times the size like this one. This one's going to be 3 times the size of that one, so it's going to look like that. So you get these integration traces that look like kind of S's with vertical bits on them. So that's the integration traces. And so this one here underneath, if we divide all of those numbers by 0.4, you'll realise you've got a 2 to 3 to 2 to 2 to 3 ratio of hydrogen environment. So you're hoovering up easy marks, even if you haven't got the faintest idea what this molecule is. You're hoovering up easy marks. Always look, by the way, those of you doing task 7 at the moment, the fact you've got 2 oxygens in there is a clue. It's often, not always, going to be a carboxylic acid or an ester. Is it not in these cases? Occasionally it's a dialcohol, or it could be a ketone with an alcohol in it. It could be something else, but very often it's an ester if it's that. But you know, you've got to have a little play. It's good fun to have a little think about it and be brave drawing molecules. Just have a go at it and see where you end up with. See what you end up with. Right, I'm going to keep going though with my little talk, if that's all right. We've done the 2 parts to it. The third part to it is the chemical shift. If anyone's got a data book I can just borrow. Now, the chemical shift you'll find on page 22 of your data book, and it will look like this. So part 3 is chemical shift. This is, it tells you whereabouts on the spectrum, to the left or to the right, a peak appears. Now if we look at those spectra I was just looking at before, you can see that the chemical shift is on the horizontal axis. I've written halfway between chemical and shift. Chemical shift is along that axis there, and it goes all the way up from usually from 0 to 10. You can get extreme examples up to like 13 carboxylic acids, might be up at 13, so let's say somewhere. But notice in the data book that hydrogens that we're interested in, or that are in that peak, are in bold in the data book. So the CH3's there. If any CH3 that's in an alkyl chain, in other words, not next to something interesting, are going to have a chemical shift at 0.9, meaning they're going to come around about here on the spectrum. Okay. A CH2 or a CH that are not interesting, the alkyl ones, are going to have ever so slightly different chemical shifts in the same region of the spectrum, but slightly different places. All of the other ones you're going to have to get familiar with by doing practice examples. But notice this CH2 is next to the carbon of an ester. This CH2 is next to the carbon of a carbonyl, so aldehyde or ketone. This CH2 is next to an oxygen, which means it's an ether. Something I would just raise there, if I could just get everyone's attention here for a second, please. Those CH2s there imply that this is only true if it's a CH2. If there was a CH3 ether, it would have a very, very similar chemical shift. So let's say I had this molecule, I don't know, that molecule, this molecule here, the kind of semi-seagull if you like, this CH3, you'll go, well, this is a CH3 ether. Let's see if I can find that on there. Well, you won't find it, but the CH2 ether will be very, very similar. It'll be in that range as well. So don't be too upset about the fact the CH2s for these. I don't know why they've done that. This CH3 could be a CH2. It would give the same chemical shift. All right. I suppose it means they might only give you questions which have these exact numbers of hydrogens in, but I don't see why they would do that. I wouldn't risk it. One to look out for is sometimes it's written as health. That's all right. You might in past papers see that as X, halogen for X. That's chemical shift. Again, that's going to take some practice. The fourth one is the most difficult one, but actually you realise that from the start that everyone got the hang of this pretty quickly. You've got to say to the examiner what you know the splitting pattern is due to. So splitting pattern. This is C data book. And you've as I said before, you're either going to get singlet, doublet, triplet, or quartet, but you need to refer to, everyone in an answer will refer to the n+1 rule. And that is a mark scheme kind of favourite. They do like to say, I know it's that because the n+1 rule. So even if you get it wrong, even if you've got no clue what's going on, at least write n+1 rule, you pick up a mark, and then guess if you have to. So let's go back to some of those molecules I drew before, and we'll talk about those, and then I'll write down what the kind of how you do it. So what you do to work out the splitting pattern is count the number of, so I'm interested in peak A, right? Which is an alkyl CH3 0.9 thereabouts, and there's 6 of them. What you do is you look at the number of hydrogens on the adjacent carbon. So the adjacent carbon is this one. Adjacent just means next door, if you weren't aware. So there's 2 hydrogens on that. 2 is n+1. 2 plus 1 is 3. So it is a triplet. So this one here, these 6 hydrogens appear as a triplet in a spectrum. And what a triplet looks like is that, 3 of them. This CH2, though, the number of hydrogens on adjacent carbons there is, the adjacent carbon is this one and this one, so it's 1, 2, 3, 4, 5, 6. Well, 6 plus 1 is 7. That's beyond what we need to know, so that one's multiplet. Multiplet, triplet, right? Make sense? These ones here, so I'm going to ask you this time, you can just do with your fingers rather than say if you'd rather. How many hydrogens are there on the adjacent carbon for these? Adjacent carbon is that one there. So how many hydrogens on that carbon? So 0 plus 1 is 1, so that is a singlet. And this one here, how many hydrogens on adjacent carbons? It's the same, so yeah, so n+1 rule, 0 plus 1 is 0, so that's a singlet. And these 6 hydrogens here, how many hydrogens on the adjacent carbon for those 6? So, close, doublet we call it. But you're right, n+1 is 2, so it's a doublet, and doublets look like that. It's like two things next to each other, kind of sticking the fingers up at you. Right, let's just do a practice a few of these. So this hydrogen's got 1, 2, 3, 4, 5, 6, 7. So it'll be a, this CH2 here would be a, which is a quartet because there's 3 hydrogens on the adjacent carbon. So I'm saying what you say in the exam paper. And A would be a triplet because because 2 hydrogens on adjacent carbon, 2 plus 1 is 3, blah blah blah. Oh yeah, you got the hang of it. Right, so let's do this one here. Shape, please. So look at the hydrogens on adjacent carbon. That one's a triplet. That one would be a. This one would be a. This one would be a. And these 3 would be. Singlet, you got it. That's it. What you need to do now is to see some real examples. I'm not going to use the video for that, but you just need to do some exercises. So I encourage you to do task 1. So I'm going to do. I'll tell you what I'll do. I'll do a couple of questions from. I'll do a couple of questions from task 1 that you can fill in with me if you've got this. So it's page 9. So I'm going to do ethyl propanoate that I'll draw for you. I don't know why I drew it so badly, but there's ethyl propanoate. So the propanoate's the bit that would have come from propanoic acid. It took me 3 lessons to do that with everybody else. I could have hurried up a little bit, couldn't I? The number of signals is the first thing, it's the number of peaks. So show me with fingers how many peaks you think there are. Yeah. And the intensity of each of those? 3, 2, 2, 3. And then the splitting patterns for those would be, starting on the left, please. This one here. Try again. quartet. These two here, quartet again, and then the last one, triplet. Now the last thing to do, I won't do this on the video because it just take too long, but I want you to see if you can look up what the position of signals for each of those would be. You're going to need a little bit of help with that. I'll come by and give you a hand with that. We'll stop there, and that's what I will share with people if you don't mind.